In order to understand radio interferometry, first you need to have an idea about angular resolution. What is angular resolution? While watching YouTube video, you might have noticed the video quality option in the settings. If you increase the video quality, the display resolution increases. That is, the image becomes more sharper and you can see finer details in it. Display resolution is similar to angular resolution. Angular resolution basically tells how well can a telescope distinguish finer details, smaller details of an object. That is, if you consider this image, as the resolution increases, you can see that you can easily able to distinguish two objects. That is, you can see finer and finer details than this object. Angular resolution is equal to some constant times the wavelength of light by the aperture size. This constant is basically 1.224 circular lengths. Here you can see that as you increase the aperture size, you get more resolution. That is, bigger the size, better the resolution, better the sensitivity. Sensitivity, the concept of sensitivity is straightforward. If you consider bigger telescopes, the light gathered is more than the smaller telescopes, and this makes faint object to appear brighter, and hence you can see greater sensitivity. Now let us consider a real case scenario. Consider an optical telescope with an aperture of diameter of 1 meter making an observation at 500 nanometer wavelength. The angular resolution attained by this optical telescope is approximately 1 arcsecond. Now let us consider the 110 meter green bank telescope, which is the largest steerable single dish telescope on the planet, and that it is observing at a common wavelength of 21 centimeter, and it has an angular resolution of 394 arcseconds. Clearly you can see that 1 meter optical telescope is 10 to the power 4 times greater than 100 meter radio telescope. So a question may ponder in your mind: is bigger telescopes better? Bigger telescopes has its own disadvantages. Now consider here the 500 meter fast telescope in China. It is fixed to the ground. You can't point it towards any desirable direction. There are engineering limitations to build a mobile telescope beyond a certain size. So then how do radio astronomers have higher resolution at shorter wavelength? Through the phenomena of radio interferometry, where many dishes and antennas acts as one big telescope. The concept is straightforward. The baseline, the distance through which telescopes are separated, acts as the size of the aperture. If you consider that this telescope is 2 meter telescope and this is a 2 meter telescope separated by a distance of 50 meter, and through interferometry these two telescopes can be acted as one 50 meter telescope, and you can see that longer the baseline, then the telescope will have high resolution and small field of view. Short baseline telescopes will have high sensitivity and large field of view. Based upon your need, you can set the size of the baseline, and there's no such thing as pizza interferometry. You can't keep small pizzas nearby and expect a big pizza. That's not possible. Okay, let's come back to here. You can see as aperture size increases, the resolution increases. This is an interferometer where each telescope acts like a single slit and creates an interference pattern, and hence you can see dark and bright fringes. The typical procedure is to find the amplitude and a phase, that is the spacing difference of this fringe pattern, to get the source brightness. The basic principle behind radio interferometry is this: Consider telescope 1 is near to source than telescope 2. To get a constructive interference, we must consider the time delay as the light traveled from the source will travel an additional distance to reach telescope 2 compared to telescope 1. And the geometric delay, which is the corresponding time delay for the signal traveling at the speed of light to reach one telescope compared to another telescope, is expressed as this. It's basic physics. You know that speed is equal to distance by time. Here, the speed and time is interchanged. That's it. Here you can see correlator. This is basically a supercomputer. This correlator actually receives the signal from two antennas and amplifies by correcting the time difference between them. Now let us consider the entire process with an analogy. Consider a crime scene where the witnesses saw something but not the whole thing and not in details. The police officer basically questions the witnesses and puts the story together. Then the detective tries to make sense of the story. Likewise, may each telescope gather light from the source where the correlator corrects and amplifies the signal. Then the resultant is examined by an astronomer. There are a lot of uses of radio interferometry. We can make an interferometer with a baseline that stretches from one side of the earth to another, and this is called very long baseline interferometry. The source is normally very far, such that the two telescopes will cause only a minute time delay, and this time delay is so small that we need a precise atomic clocks to measure, such as hydrogen maser clock. The accuracy of this clock is 1 second in 1 million years. VLBI helped us to take the first image of black hole, supermassive black hole at galaxy M87. VLBI also helps us to get the precise value of Earth's rotation and tilt. The Earth's rotation is influenced by a lot of factors. So we can find the Earth's rotation and tilt by observing a distinct quasar which are fixed and stable in the sky using radio telescopes located at different parts of the world. We can use the difference in time delay to get the exact value of the tilt and rotation. VLBI is also used in the world's most powerful radio telescope, square kilometer array. The basic technique is VLBI. Nearly 1 million low frequency antennas is going to be installed at Australia and thousands of high frequency dishes at Africa by 2027. The future in radio astronomy is still wide open for you to make great discoveries. Thank you.